For a two-terminal resistive network, these sets of measurements are available. We need to find the Thevenin's theorem for the network. So the terminal voltage is the two terminal voltages that are measured is 12 volt and 0 volts, and when the terminal voltage is 12 volt the current is 0 amps, and when it's 0 volt it's 1.5 amps. So when we look at this set of measurement, the first one, we can see that the current is 0. That means there is no flow of current, and the voltage, there is a voltage reading. That means this is the open circuit condition. So if we think of the network, it's a resistive network with source, whatever source is there, and this is the open circuit voltage there. So that's the reading there, and there is no this is open, that's why there is no current. So this one is the Thevenin's voltage as we know it. So that's the Thevenin's voltage, which is VOC, which is 12 volts. So we can get that. And then when we look at this measurement, it's 0 volts and there is a current. 0 volts means this is essentially short circuited. So that is the current that is flowing is short circuit current. So we have two currents, short circuit current and we have short circuit current and open circuit voltage. Now the open circuit voltage means that the maximum voltage that the network can offer to any load when the load is connected. But this is before the load is connected, because when the load will be connected there will be flow of current and there will be some internal drop. So without that, that's the maximum possible voltage that the network can offer to a load. So if we think of the Thevenin's network, Thevenin circuit, which is like this, and there is the load that is connected. So this one, as we know, replaces the entire remaining part of the circuit, and this is our resistance of interest. In this case, this will be the load. And when it is not connected, so this is Thevenin's voltage and this is Thevenin's resistance, we know that, and this, let's call it RL. When it is not connected, the voltage that is available here is V Thevenin, because that's the open circuit voltage. But once this is connected, there is a flow of current and there will be an internal drop. So the resistance, the voltage across the resistance actually V Thevenin minus I, if the current is I, minus I turns R Thevenin. So that's the drop as given by Ohm's law through the across the resistance. So that's the open circuit voltage, which is the maximum possible resistance, maximum possible voltage that the network can offer to a load. Similarly, the short circuit current is maximum possible current that the network can offer to a load when the load is minimum, because if it is not connected, if it is load is 0 still, here also load is 0 because it's not connected when we are talking about voltage. When is a short circuit current means that the load is connected but it's 0, so load is minimum. So the maximum possible current that the network can offer to a load, that's the short circuit current. So maximum possible voltage divided by maximal possible current. That means if the load was, let's say if the load was 0, this is the maximum possible current. So if we look at this one, we can see just now that the maximum possible voltage divided by the maximum possible current, which is the open circuit voltage divided by the short circuit current, is the Thevenin's resistance, because when the load is connected with a finite value of resistance, there will be an internal drop, and that drop will be because of the resistance, because of Thevenin's resistance, the drop because of Thevenin's resistance. So R Thevenin is VOC divided by I short circuit. This is another way to calculate actually R Thevenin's, because the maximum possible voltage that the network can offer to a load divided by the maximum possible current that the network can offer to a load. So when we divide this, we get R Thevenin. So we have here V which is 12 volts here, and this is 1.5 amps. So this one is volts, amps, so this one is 8 ohms. So that's the Thevenin's resistance in our Thevenin's equivalent circuit. So just from these two measurements, we can find actually Thevenin's equivalent circuit for any given network.